All right, section 5.2, multiplication and division of integers. We started this section last time. We had gone through the models of multiplication, talked a little bit about what multiplication was, and we had done, I think, a couple of theorems maybe. Nope, we didn't. We hadn't gotten that far yet. We talked about what integer multiplication looks like with positive and negative numbers specifically and how they're related. And then we were on to the point of talking about the properties, which are theorems, basically, of integer multiplication. So we've done this recently. This is all related now to multiplication, so I want you to fill in the blank with what you believe to be the theorem that it's referring to. The first three we've seen before with whole numbers. The next three we've also seen before with whole numbers, so you should be able to fill all those in with at least a pretty good idea, remembrance of what those are. So fill those in, and then we'll double check that everybody has the right details specifically written down. What'd you write down for closure? Closure is that weird property. I know that some of us feel a little uncomfortable with it. But what did we write down for closure? Do you remember how that works? What'd you write, Kaylee?
I wrote A times B equals C.
Okay. So not necessarily C, or we could say C. We don't need it necessarily there. But A times B is a specific kind of number. What will it be?
Whole number?
Not whole number necessarily.
Integer?
But it'll be an integer because we're talking about the integer system. So when I multiply two integers together, I get another integer. So we'll use a little bit of symbols. Actually, I don't know that I've used them in this class quite this way, so let me just write it out. This is a unique, and it is unique, so a unique integer. So if you wanted to say equals C, where C is a unique integer, that'd be fine too. Okay, what's the second one? The commutative property. What's that say? Someone else. What do you have, baby?
A times B equals C and B times A equals C.
A times B equals what?
C.
Okay, and then what?
B times A equals C.
Okay, so they're equal to each other like this, right? Okay, so we could put the equal C between them, or we could leave it out either way. The point being that the order of the multiplication doesn't make any difference, right? That's the commutative property. Everybody good with that one? Okay, now associative property definitely needs an A, B, and C in order to even talk about it. So what do I do for the associative property? Do you want to do this one, Amanda?
Yeah.
Okay.
So AB in parentheses times C
Okay.
equals A times BC in parentheses.
It's all good? Okay, great. All right, so those are the first three. Those are the three that have been present in every number system that we've looked at in this class, right? I mean, the whole numbers, we talked about them there several times. We did it with addition, and we did it with multiplication, and now we did it with addition again, and now we've got a multiplication again. There's a version of it for all of them. All right, the next ones don't necessarily happen in every number system. I'm sorry, the first one does. The next two were a little bit different. So let's take a look at the first one, the identity property. What is the identity property of multiplication of integers? Thank you, Kaylee. A times 1 equals A. There's another part to that.
Equals 1 times A.
Right. We want to do the multiplication in either order. We kind of get it for free because of the commutativity part of the fact that multiplication is commutative, but we do want to recognize that this works in either order. And this number 1 is unique. That is, it's the only number that does this. There's no other number that has this ability within our number system. Okay, distributive property. This is unique because it has to combine addition and multiplication. It's the only one that does, right? All the rest of them were specific so far, specifically about multiplication. This one combines multiplication and addition together. And there's two parts to it. So one of the parts starts out like this, and the other one starts out like this. I don't care what letters you put or where you put them necessarily, but one of them has the multiplication in front and the other one has the multiplication in back. Make sense? So somebody tell me what the first one ends up being when I distribute. AB plus AC? Okay. Somebody tell me what the second one would end up being.
CB plus CA.
Okay, I'm going to write it in the other order, but yeah, CA plus CB. Just going to move from left to right, okay? And we, of course, have done this sort of idea where we've drawn, like arrows or curves showing the multiplication that's going to occur. The zero multiplication property. What does that say? We saw this once before.
A times 0 equals 0 times A equals 0.
And the zero doing this is also unique. In other words, no other number has the ability to be multiplied by A and give you 0 as an answer. So 0 is the only one that does that. So this is the zero multiplication property. All right, so take a look then at the next example. You're going to decide which property is being used in the first of the in these 4 of them. So take maybe 1 minute and fill in the property that you think that best describes this, and then we'll have you check with a neighbor and make sure that everybody has the same thing. So once you're done filling it in, ask your neighbor if they're done too. You guys want to powwow just for a sec? Okay, so I'm seeing lots of nodding heads. So either we're all right or we're all wrong is what I'm guessing, right? No, I'm sure that we've got most of them right, or all of them. Okay, what was the first one? That is closure. This was the symbol I was avoiding using earlier because I couldn't remember how frequently you've done so. This means, do you remember what this means, that symbol? Is an element of. We use it more in the number, or in chapter 2 of this class, way back when, right? It's been a while since we've actually used it. So, is an element of, good. And then I is the integer. So what's the second property? The zero multiplication property. How about the third one? That's distributive. And the fourth one? What's it? Commutative. Good. Easy peasy, right? Good job, guys. All right. So there's a few more theorems that we're going to encounter, and then a few more. There's quite a few more, actually. Then we have one more example. So let's take a look at some of these theorems. I bet you can fill in what some of them are, but you may not have exactly the right details, so let's do them together. All right, so the first one says, Theorem 5.6, for every integer a, if you have negative 1 times a, it equals the negative of a. I actually talked about this with one of my students. They were looking at order of operations something, and they were talking about exponents, and I told them, a negative a is really just like multiplication. The negative is being multiplied by what's next. Okay? So we have negative a. Theorem 5.7 tells us that if we have negative times the a, in parentheses, times b, it's almost like I've got an associativity. I can take the negative and I can put it on the outside of the parenthesis, because it's equivalent to having negative 1, and I can associate the a and the b together. And that's actually how you think about multiplication. You do not have a multiplication table of negative numbers. You don't, right? Because you don't need them. You can use everything you know about positive numbers and simply put the negative on when you need it. So that's what we do. The second one, and that one underneath 5.7, says that if you have two negative numbers, what's a negative times a negative? It's positive, right? We talked about that from a CHIPS model, from a number line model, and from a charged fields model last time. Why that would actually work, that a negative times a negative equals a positive. All right, so theorem 5.8 talks about distribution, but it talks about distribution with subtraction, okay? I don't know why they decided to separate it like this. Back when we did whole numbers, they put it together with the distribution property. I don't know why they did it here like this, but they did. So we've got the same distribution property we saw earlier. It's just with subtraction instead of with addition. Okay? Everybody good with those? I don't want to rush anyone. Does everyone have them written down? Are you good, Jillian? Okay. All right. Okay, let's take a look at the next set. All right, we're going to move on into division and look at some theorems with division. So the first one says integer division, and this is much like whole number division when we saw it earlier. For all integers a and b, a divided by b equals c if, I think that should say there exists, if, I'm not even sure how to reword that. That's not worded right. If it exists. See if it exists. That's what's the problem. I think I'm missing a comma on the paper. No, I'm not. I just didn't read the comma. Okay, let me start again. We'll go back and try that over. All right. For all integers a and b, a divided by b is the unique integer c if it exists. That is, if the c value actually exists, such that a equals b times c. Okay? So if you think about writing it out more like an equation, you can see it a little bit easier what they're saying. If you have a divided by b and that equals c, if you think about this maybe in a fraction way, you don't necessarily have to do fractions, but one of the ways you probably did at some point looked like this. And you did something called either cross-multiplying, or you simply recognized you'd multiply by b on the bottom to move the b over to the other side. And then this a would equal c times b, or b times c. And that's exactly what you have at the end here. A is equal to c times b. Now, from a number sense, this is exactly how you define division. We've talked about this once before as well, but let's do it again. And I'll just use whole numbers, not because integers don't work, but because it doesn't matter which one we use. So if I did 5 divided by, I don't want to do 5. Let me use 6. 6 divided by 2. We know that 6 divided by 2 is equal to 3. And the reason is because it's the same thing as asking us 2 times what equals 6. What's the missing factor when I multiply by 2 that will give me the answer to 6, the answer of 6? The answer, of course, is 3. That's all this definition is saying. It's saying what's the missing factor in multiplication? That's going to be my division quotient when I'm done. Okay? All right, so divisibility. We talked about divisibility in Chapter 4 a lot, didn't we? A lot, right? We talked about how we know if a number is divisible by 2 or by 3 or by 6, how we know if a number is divisible by 5 and by 10 and so forth. So this is talking about divisibility now with integers. In particular, that means it must be talking about negative numbers because we didn't have that property before. If a divided by b is a unique integer, then a is divisible by b, or equivalently b divides a, and it's written b, that little division sign, right, that divides by sign, and then the a afterwards. Basically what this is saying is that everything you did with divisibility of whole numbers works the same for divisibility of integers. So for example, if you could talk about 6 and you could divide it by a negative 2, what is 6 divided by negative 2? What is it? Negative 3. Okay, so it satisfies this criteria. A divided by b is a unique integer. What that means then is the a value, 6, is divisible by b. Is 6 divisible by negative 2? Well, of course it is, because it gave me an integer when I was done. Or equivalent, we could say that b, that's the negative 2, divides a, 6. So does negative 2 divide 6? Sure it does. Okay? So that's all the same notation and language that we used when we were doing division with whole numbers, and divisibility with whole numbers. All right, inequalities. Integer inequalities. 2 more after this. For all integers a and b, a is less than b. We write that, of course, with the less than sign between them. If and only if there exists a positive integer k, such that a plus k equals b. This is the exact same definition we had for whole numbers. It's not one bit different. but it's doing it now for integers. It's saying that, for instance, if I had -2 and I want to say that -2 is less than 1, how do I know that? Well, I know it because there's a number that I can put here and add it to the 2 to equal 1. What would that number be? It'd be a 3. So the 3 is the k value they're referencing. And it has to be a positive. But what happened if it were a negative? What if it was a negative that was supposed to go in that blank instead? Would it be less than? We can try one. So if I wanted to say that I had A less than B, and there was a negative number here, and so for the sake of argument, I'm going to write it in as a -c, just so that we can think about it that way. Okay, so C itself is positive. The negative is indicating the fact that the whole number is going to be negative. What's going to happen when I take A plus a -c? It's like subtraction, right? Is that number going to be smaller than A or bigger than A? Smaller. So that's the reason this says that there's a positive integer. Because when I'm adding the positive integer, it gets larger to actually equal the B on the other side. If I'm adding a negative integer, it would be getting smaller. So we don't want there to be a negative integer in there. It needs to be a positive integer in there for that to actually work. All right, there are two integer inequality theorems, Theorem 5.9 and Theorem 5.10. So Theorem 5.9 says the following. For any integers A and B, A is less than B, or equivalently B is greater than A, if and only if B minus A is equal to a positive integer, i.e. B minus A is greater than 0. Okay? We had a property like this for whole numbers as well. The only way that -2, I'll use the same ones I did before, is less than 1 is if I take 1, the one that I think is larger, minus the one that I believe is smaller than -2. The answer to this needs to be a positive number. Right? If you take a bigger number minus a smaller number, you better get a positive number. The distance between them, right? So what is 1 minus -2? It's 3. And that is, in fact, greater than 0. What would happen if it was equal to 0? It wouldn't work. Why? What could we say about those numbers? Yeah, they're the same number, right? The only way this is going to be equal to 0 is if I've used the same number twice, right? 3 minus 3. That's how I get 0. Okay, so that's why it's greater than 0, not like greater than or equal to 0, right? All right, two more here. Apparently I left my A and the B off when I did my slides here. For all integers A and B, it's not A and B, I'm sorry. I got carried away. So many A's and B's. It should be X, Y, and N. That's what's there. That's what's in your paper. So we have integers X, Y, and N. If X is less than Y, then X plus N is less than Y plus N. We had a property like this for whole numbers. The property still holds here, except that that N can be any integer, so it could be a positive number or a negative number. So if you add a positive number to both sides, the inequality stays preserved. If you add a negative number to both sides, the inequality is preserved. You guys with me? Doesn't matter what you add, it's the same thing. All right, the next one says, though, that if you multiplied by a negative, the sign or the direction of the inequality changes. This is one of those things that people sort of vaguely remember, but when they're working a problem, they sometimes forget to do it. They'll multiply or they'll divide by a negative, and they'll just forget to do the change of signs. Let me just show you why it's true with with a number example, because sometimes it feels like one of those mysterious things that we just do it because somebody told us we were supposed to, and it's really quite easy as to why it works. So let's just start with a very simple 1 is less than 2. Everybody's good with that, right? 1's less than 2. And let's multiply them both by a negative now. And let's think about a number line. So on a number line, here's 0, here's 1, here's 2. 1 is definitely less than 2. Where's my -1? Well, it's over here, and here's my -2. Which number is bigger, -2 or -1? Negative 1, because it's further right on the number line. A number that is further to the right is a larger number. So very quickly we can see with a very simple example that that inequality had to switch, right, for that to work. All right, the next one is telling us, however, that if the n integer itself was positive, then we could multiply on both sides and the inequality would be preserved. All right, so if I multiply by a 5 on both sides, so let's just use the example I gave, 1 is less than 2. If I multiply 1 by 5, I get 5. If I multiply 2 by 5, I get 10, right? The inequality stays the same direction, and it works for all positive numbers when we multiply. What do you think is going to happen when we multiply by a negative? Because that's the last piece here. It's going to flip it. So for the exact same reason we already did that before. So this is going to be x times n is greater than y times n. So the inequality switches. Okay, I don't have any examples in here with inequalities, but I do have a couple of examples with equations we're going to look at as our last thing today, and then we'll do some group work. All right, we're going to find all integers x, if there are any, and there don't always have to be ones that work, but any integers x that make each of the following statements true. So you're welcome to use algebra to simplify this. You're welcome to think about it from a trial and error kind of perspective. That's okay too. There's nothing in here that says this is the only way to solve this problem. Okay? So let me show it with you with sort of thinking through it without the actual detailed algebra. If you take a look at the first one, it says negative 5 times x minus 3 is equal to negative 5. And do you see how the two negative 5s, they match? Are you guys with me? If that's the case, then we already know that this piece and this piece are equal. So what does that tell me about the piece that's in parentheses in order for this to actually work? Everything in that yellow orange circle has to be what? It has to be 1. It's a property of multiplication, right? The only number that I can multiply negative 5 by and get negative 5 is 1. So that x minus 3 has to be 1. So what would I have to let x be in order for x minus 3 to be 1? It'd have to be 4. You see how we reasoned through that? You don't have to do it this way. I just want you to see that that's a possibility. And you're going to have kids in your class who are going to do that on a problem like this or on other problems, and you're going to have to think through whether that's okay with you. I mean, sometimes that's okay. Sometimes it might not be, because this was very unique, wasn't it? I mean, what if I didn't have the negative 5 and the negative 5 that matched? Oh, this wouldn't quite work, would it? Okay, so this x value is equal to 4. Let's do the same problem and sort of multiply it out so that we can see those properties in action now. So this is the other version of the way to deal with this. So we could use the distributive property, right? Okay, so if I use the distributive property and multiply this through, what do I get on the left-hand side? Negative 5x plus 15. So those use two properties of integers, a negative times the positive version of x. So that's negative 5x, and then the negative 5 times the negative 3 would be the positive 15. And that's equal to negative 5 on, negative 5, get it written right, on the right. What would we do next to solve this equation? We would subtract 15. Very good. All right. So this adds to 0, which was the whole point. That's an additive property of equality. And then I've got negative 5x on the left. What is negative 5 minus 15? That's negative 20. Those are using properties in 5.1. Okay. Then what would I do to get x alone? I would divide by negative 5. So a negative divided by negative is a positive, and 20 divided by 5 is 4. So this is positive 4 from a very algebra manipulated point of view. Okay. Let's do the same thing on the next problem. Let's think through it sort of logically about what's going on, and then we'll go through the algebra for it so you can see how to do it from that perspective too. And then you guys can choose how you'd like to do them. It doesn't matter to me. All right, so this first one says, or this problem says, x minus 1 squared on the left, and it says 1 minus x squared on the right. So tell me what you see that's the same on both sides. The squaring. That's true. The squaring's the same. Okay? What about inside those parentheses? What do you notice? They flip them. I mean, it almost looks like they're trying to do something with commutativity of subtraction or something like that, right? One's 1 minus x, the other's x minus 1. There's a relationship when you subtract things in different orders. Do you remember what it is? Right. So if we just took, let's just do an example real quick. Let's do some numbers. We tried this before when we tried to see if there was commutativity subtraction. We did something like this. Let's compare 3 minus 5 and 5 minus 3. Same numbers, but the order in which they're subtracted is reversed. 3 minus 5 is negative 2, and 5 minus 3 is positive 2. The numbers are exactly the same. It's the signs that are different, right? Everybody remember that? So what's going to happen inside these parentheses when we subtract? No matter what x is, what's going to happen? You're going to get the same thing inside, right? But the signs might be different, or will be different. But then we're going to square it. So what's going to happen when we square it? Everything becomes positive. Are you guys with me? I think, maybe? We're okay? All right. So no matter what number we put in on the inside, one of them is going to be positive, one of them is going to be negative. So let me just write one down here, sort of conceptually what we're saying, that this is a positive number squared, and it's equal to a negative of that exact same number, whatever it is, squared. The numbers are the same. The signs are different. But when we square them, what happens with my signs? They're all the same, right? They're both positive now on the sides. What happens to the numbers? They're the same because the numbers were the same to start with, right? If you had 5 in both of them, one's positive, one's negative, and you square it, you both get 25. So what does that tell you about x? This might be the biggest leap of the day. What's my answer? It's what? Yeah, so in particular we could say something like it's any integer. Any integer in there will work. Because no matter what happens, when I multiply, when I square, let me say it that way, when I square both sides of numbers that are the same, but they're additive inverses, right, same number but opposite signs, I get the same value. Okay? All right, so let's do it from a manipulation point of view, like we're going to manipulate the values themselves. This is harder to see because of the squareds. So I'll show you what I mean. All right, so the first thing we're going to do when we have squares on both sides is what? Any guess? Yeah, we can take the square root. Yeah. The way we undo squaring is we take square roots. Here's the catch. When you put a square root into a problem where it did not exist before, you have to put a plus or a minus with that square root. Now, there's a square root on both sides. We don't need a plus or minus on both sides. One plus or minus will do just fine. Okay? It takes care of both possibilities. So on one side I have x minus 1. On the other side I have a plus or a minus and 1 minus x. I have two possibilities now. So in particular, what this means is that I have two equations that I can write out. One of them says x minus 1 equals 1 minus x. The other one says x minus 1 equals negative 1 minus x. Are you guys with me? Everybody good so far? All right, we'll just go from left to right. We'll start with the left one. What am I going to do to solve this one that's on the left? Okay, add a 1 to each side. So that'll add that. So now I've got x equals 2 minus x. Is that okay? Now what? Add x to both sides. So now I have 2x equals 2. And then what would I do? Divide by 2, so what would I get? X equals 1. And does it make sense that x would equal 1 and that would work? I mean, like, just think about the numbers themselves. What's going to happen if I put the number 1 in? I get 0 on both sides, yeah. So 0 squared on both sides, yeah. Okay, so x equals 1, definitely a possibility. Over here, I've got x minus 1 equals, and then I need to distribute the negatives. This is negative 1 and plus x, right? If I reorganize this, I can move this so that it now says x minus 1 on the right as well. Are you with me? It's the exact same thing on both sides, right? If it's the exact same thing on both sides, then x could be any number and make it true. So here's where we get the x is, I'll use it now, an integer. We'll write that way. So do I really need to write x equals 1 and x is an integer? Well, no, because 1's an integer, so we're good leaving out that actual specific example because this actually takes care of both cases of it. All right, any questions on that one? I know that's a weird one, but that's not why I chose it. I wanted to make sure you saw something that was a little weird.